Projectile motion. Projectile motion, just think about an object moving in 2 dimensions. It makes it a little bit easier. The definition your book gives, and I'm trying to be consistent with your book, is a free fall, but with an initial horizontal velocity component. So meaning an object that is kind of dropped, but it might also just be pushed off the edge. Or an object that is kicked at some sort of an angle. So just think about when an object is moving in 2 dimensions, it's projectile motion. In 2 dimensions, not just up and down, or not just left and right, but maybe moving left and right and up and down at the same time. Or like this. Okay, it's a projectile motion.
Wait, would a projectile motion be like, say, you were on a cliff and like the cliff was straight and you kicked like say like a soccer ball and then so it went straight for a second and then it dropped.
Yeah, exactly. Very good. Because it's moving where? In the x direction. It's moving in the x direction like this. It's also moving in the y direction like this. So because it's moving in more than one direction, we consider it to be projectile motion. That's
So like if it's going at like a diagonal,
yes.
then that's it.
Exactly.
Like even toss the ball straight up in the air, straight up is only 1 dimension.
So we don't call it projectile motion, we just say one-dimensional
Just
motion.
projectile.
The object is still a projectile. So for the most part, when we say projectile motion, we're talking about 2 dimensions. Because this is just linear motion. One-dimensional linear motion up and down. But when it's falls like this, it's projectile. Okay? Gabby? Think of basketball or football. Think of any sport really. Anything in any sport. Unless like, for example, baseball is not as much a projectile from a pitcher because it's more of a line drive. But a pitcher throws a pitch. I mean, unless it's throwing a curveball. After you hit it, it's different. But from here to there, a changeup or a fastball, they don't have any movement on it. Curveball dips, slider curves in, knuckleball knuckles, a split finger drops. But a circle change drops. Changeup doesn't drop. I know baseball. A changeup doesn't really drop. Okay, maybe a softball, sure. But traditionally, for projectiles, think about an object that's hit at an angle. So after the baseball is hit, so he hits it out of the park, say it's a home run, then in that sense you want to consider that to be like a projectile. Okay? So when you're not looking at 2-dimensional motion, go back to the stuff we've done. But when you see an object moving in 2 dimensions, think about projectiles. Okay? Think about projectiles.
Are you a Yankee fan?
I'm a Met fan.
Mr. Howell, so am I.
You guys are doing so well this season.
I'm a Met fan.
They do so well.
And I'm a Jet fan also, so I don't
Yeah, Jets are doing really
I don't
good.
think winning teams.
Yeah.
You know?
Yeah, seriously.
Are you a Knicks fan?
I mean, I am by default from New York, but I follow college basketball. I don't really follow pro basketball. All right, let's take a look at these 2 different examples here. First,
When you're going to take that picture again.
imagine we have a runner, okay?
Guys, look, it's Helen.
You have a runner, and the runner, I don't know why that's Helen, but
It's Helen's brother.
okay, Jim, focus.
Helen and scream.
You have a runner. The runner's running, and he or she decides to do a long jump. You know, remember a long jump is where you're running, you have to jump as far as you can go. So, while you're running, you're only moving in 1 dimension. You're moving left to right, that's it. But the minute you jump, now you're moving up and down, and you're moving left to right. So this first one, A, is 1-dimensional motion, which is what we've studied. This part B is 2-dimensional motion. And look at the velocities. Here, your velocity is only in the x direction, so you simply have a v there. We can say that v is really just vx. Okay? Obviously, the board,
Can you
Sorry.
just that?
the board isn't calibrated, guys. That's vx there. Okay? But when you move in 2 dimensions, you not only have a velocity this way, but you have a velocity up and down also, because you're moving up and down. Whenever you're moving in a direction, you have a velocity. Movement indicates velocity automatically. So if you somehow move vertically and you're moving horizontally, you must have a velocity in the y and in the x. And this is what we talked about yesterday with the triangles. Vx comes about using the cosine, Vy comes about using the sine. Okay, whenever it's at an angle. Is that clear? Anything necessary? Remember, Vx is cosine, Vy is sine. So the difference here, this is 1-dimensional motion, this is 2-dimensional motion. Okay? Alright, next. Come on, I'm just trying to explain so you're used to it. On the right side, because the person is moving not only left to right, but he or she also jumped. So he's moving in some sort of a parabolic speaking. Let's go into realistically speaking. Oops, wrong way. There we go. The blue dashed line that you're going to see here. Okay, the blue dashed line. Eric, is this you because you're soccer now? Is that what you said? The blue dashed line, which says black, which says A, it says A. It's like
Racially welcoming.
black or white, just an Englishman thing. Doesn't matter, right? Come on, guys, please. I hope we're over that. It's one of my favorite songs, by the way, Michael Jackson.
Black or white? Do you like MJ?
I am a big fan of it.
You should be MJ for Halloween.
For Halloween?
Yeah.
Do you guys get dressed up here?
The teachers do.
No.
You just tell me that, so I'll do it.
Imagine if you been dressed as Michael Jackson.
I usually do get dressed up for Halloween. I usually do wear some sort of like. I'm not gonna do it.
Miss Starks did it last year.
I usually do something corny, like I'll be like
Just wear one white glove. Wear one white glove.
It's usually like no, it's usually like a scientist.
No,
or something like
teachers
that.
usually dress
Oh,
up
you're
for
lame.
Halloween.
No, they don't. But seriously, just wear one white glove. They can't take anything from you. Like I'm a germaphobe. I'm a germaphobe with my left hand.
Oh, yeah. Anyway,
I'm hot.
the blue pen you guys see here at the top, that's a perfect parabola without any air resistance. But think about logically speaking. If you kick a soccer ball, the wind is going to slow it down. You've seen that before.
Actually,
If you ever played like a really windy day, you notice the wind affects the movement. So with air resistance, the projectile will not go as far. So part B here, or sketch B, is with air resistance.
So it's like, it's basically like reality and.
Yeah, this is reality right here, path B. This is optimal for us for physics because we don't worry about air resistance. If we looked at air resistance, we would have to use some sort of calculus to use the equations. So we're simplifying it and we're saying without air resistance. Okay? There's going to be rarities that I'll say we're using it, but not for projectile motion. Okay? So we're saying there's no air resistance, no air resistance. Okay? So the blue pen is our general one. I forgot tennis balls. Hold on. Give me 1 second.
You're like, ew.
Guys, we're recorded right now. Okay, we let me have one.
Have one of what?
Guys, we're not supposed to eat in class.
Sex, I'm eating the Oreos in class. I'm hungry.
Give me a look.
You know you're being recorded, right?
Yep,
Yeah.
that's why I said that.
I was wondering who had done this.
Are those apples?
Oh my cover.
Can you?
Your cover was blown like 20 minutes ago.
You won't pay that.
Do it.
You're playing beer pong?
Now,
So it's
here's what I want to talk about. And this is kind of a weird phenomenon, and I want to get a hypothesis for the class. What I'm going to do is the following. I'm going to take this tennis ball and roll it off the table, just at some velocity, doesn't matter, fast or slow.
Then you're gonna bounce it.
The other one, though, what I'm going to do is as soon as this one leaves the table, I'm going to drop this one. Which one's going to hit the ground first?
the one you just dropped.
The one I dropped?
I'm gonna go. Oh, they're hitting at the same exact time.
Same time.
Same exact time.
Look at his lights, his eyes light up at the same time. He's yeah!
The one you
I
drop.
like the intuition. I'm going to drop.
I like those
I think
Oreos.
they're gonna fall.
This is kind of weird because if you think about it.
No.
Ready? Here's what I'm doing. I'm rolling this one off and I'm dropping this one. And I said with any velocity. So what this means is that, imagine if I had, John, thanks for the recording and stuff.
Oh.
Imagine I had a bow and arrow, and I shot a bow and arrow perfectly horizontal. And at the same time, as I released the bow and arrow, somebody else dropped, say, like a quarter. Okay? It's the same thing as what I'm doing right now, actually. I'm modeling that with simple tennis balls. But you see what I'm saying? If I shoot a bow and arrow horizontally, it's like this one being rolled off the table horizontally, as opposed to me just dropping this one over here. So it's the same thing as shooting an arrow and dropping an object at the same time. Which one will actually hit the ground first?
They'll hit at the
And
same time.
you're going to say right away that this one dropped is probably going to land first because you would think an arrow would go pretty far, right? But again, I'm shooting horizontally. Okay? So, you can't see it, I'm going to stand up to that.
Faster speed.
So what I'm going to do is, as soon as this tennis ball leaves the table, I'm just going to drop this one. You want to help me?
Yes.
All I want you to do is go like this. no bounce, and I don't want it to slow, I want it to roll. Does that make sense?
Yeah.
So, as soon as this, and just back up, switch over.
I do whatever I speed I want.
Well, in the beginning a little slower, and we can get faster.
Alright.
As soon as the ball leaves the table, I'm going to drop this object from the exact same height. So watch what I'm going to do. I'm just going to go again. Everybody see that?
Want me to say go? Want me to say go?
You can say go, but I'm going to watch also.
Go, Helen. Go, Helen.
Go, Mr. Howell.
Anybody notice what happened there?
Same time, exact time.
And they hit the
Riddle
ground
me
at
that.
the exact same time.
Riddle me that.
Riddle me
Stop
that.
signing me riddle me that.
Riddle me that, okay?
All right, now, Helen's going to try and toss it a little bit faster to show you that it doesn't matter what velocity. See that? Woo! All the way out there. They landed it all the way out here. About 10 feet away. But they still landed at the exact same time. Now, with that,
Wait, how about? Oh, well, I guess you couldn't do it then.
if you toss it at an angle, it's not true.
No, I
It's
was
got to be perfect.
Oh, yeah, no, because I was gonna say, how about if we both?
Why?
No, well, it doesn't make sense actually. No.
I mean, if Helen theoretically was able to toss the ball like this, perfectly horizontal,
Oh, we can do it.
and at the same time she released it, I dropped it from that height up here. The ball, the time it takes for this ball to hit the ground, her tennis ball would travel X amount that way, but also hit the ground at the exact same time. Say again?
He's saying hypothetically, not actually. Because it's going
There might be like a small discrepancy from air resistance of her path, because hers is more air resistance. But theoretically, without air resistance, they're going to hit the ground identically. And that's what I'm going to explain why next.
So why
Right?
is
And I'm going to go into why.
Is it because it's faster?
No, it doesn't, and that's the thing, the speed is independent. It doesn't matter if the velocity horizontally is 10, 20, 30, 40, 50 miles per hour, it makes no difference.
It's just because like going horizontally doesn't affect it at all. It doesn't affect
What?
um,
What is this called?
The drop.
Vertical motion. Very good, that's exactly why, Tom. And I'm going to go over that now. What Tom said is good. He said horizontal motion, if you have only horizontal motion, it doesn't affect the vertical motion really. It's like they're separate entities. And that was that word coupled and uncoupled. That's where we're going to get into that. So what I want to do now is show you exactly what I'm saying. Imagine you have a cliff. So everybody draw a cliff, please. Out here you have some water.
Should we draw this?
Yes, please draw a cliff. Now, we've got a projectile at the top of the cliff. And let's say it's a soccer ball. And Erica's at the top there. And she kicks the soccer ball off the cliff with only a horizontal component. So she kicks it as if she were passing it. So when you pass to somebody, traditionally, say you're passing on the ground, you use your instep, right? And you want to keep the ball nice and flat along the ground. You don't want to pass it to somebody and hit them in the leg or in the knee because it's harder to trap the ball. So you want to hit it only horizontally. So Erica comes up to the cliff. She steps up here. Oops, her body's kind of awkward because the smart goes on. Sorry, Erica.
We're gonna draw her shoulders.
You have to make her what?
Short.
Alright, yeah, I can see the
Let's not draw person because it's going to go
Draw
on.
her shoulders.
So the ball is kicked off the cliff perfectly horizontal. Okay? Now, it's kicked perfectly horizontal, but eventually what's going to happen to it?
It's gonna start dropping.
Yeah, it's going to start to drop in some sort of a parabolic fashion.
Drop the beat.
Okay?
The ball.
Now,
We can only use the word.
initially, why don't we lower it? We can lower it. Let's shut it off for a few minutes, huh? For a few minutes, maybe we'll put it back on.
Super hard.
So, we have an object kicked horizontally off the cliff. Again, only horizontally. Now, when the object reaches this point on its path right here, when the object reaches that point on its path, we want to think now about what kind of velocity it has. It's got initial velocity pushed in the x direction from the kick, but then it starts to fall. So it starts to pick up speed on the way down, like an object that was dropped like this. Initially, it's at rest, my pen in my hand. When I drop it, it picks up speed because gravity pulls it down. So that's what's happening here. So initially, this velocity is only in the x direction that she kicks it with. But then later, it still has an x component of velocity, but now it's starting to pick up velocity in the y direction. So now we have both components. And this is where our triangle came into play, if you remember from trig. We had the x component and we have the y component. As it gets further and further away, or gets closer and closer to the water level, it's going to pick up more and more speed in the y direction. In the y direction. How come it picks up speed in the y direction?
Gravity.
Gravity. And we know that in the y direction, okay, we have an acceleration of negative 9.81 meters per second squared. And I'm going to put a little subscript in here, and put a little y there next to the a, indicating that that's an acceleration, but it's acting in the y direction. Because nowadays, now that we're in 2 dimensions, if I just say acceleration, you don't know whether it's left to right or up and down. There's no way to denote that, except by putting a little y there to indicate the vertical direction. Now, if I were to look at the projectile at this point on its path, oops, the red marker just never works, man. It's weird. I remember that instrument. It's got a bigger component of velocity, and it's still got its horizontal component of velocity. Because it's picking up more and more speed downward. But here's my question for you. After Erica kicks the ball, is there anything that's really pushing it in the x direction anymore? Air is slowing it down, actually, right? I mean pushing it.
No.
Pushing it.
The
No,
force is
right?
getting pushed.
So Erica kicked it with some force, but after she kicked it, the object just has momentum at that point, and it just carries outward. But it's not gaining velocity in the x direction. There's nothing pushing it. There's no rocket boosters on the back of the soccer ball that are directing it forward anymore. So this Vx that you keep seeing, this Vx is the same. It's not changing because the acceleration in the x direction is 0. There is no acceleration in the x direction unless it has rocket boosters on the back of it, or unless somehow there's a magnetic field that like pushes it that way, but we haven't even got the magnetic fields. This is just going through normal space here. Okay? So what we can say, what we can say here is that the velocity in the x direction is a constant. And a constant means it is not good, not changing. Whereas the velocity in the y direction is different. Initially, look at this object here. Look at this object, it's pushed outward, or it's pushed horizontally. So there's no vertical velocity at all. It's only in the x. But then you notice, isn't there a vertical velocity as we go down?
Yeah.
So what we can say in the y direction is that the VI in the y is equal to 0. And notice I'm putting more subscripts nowadays. Normally I would just say VI is 0. Remember when I drop this pen, I drop it from rest. So VI is just 0 at the top. Now I need to specify. I'm talking about VI, but in the vertical direction. So I put VIY equals 0. Okay, initially. These are 2 key points that we're going to use today. Okay, that we're going to use. When an object is launched, and we're looking at only horizontal today. When an object is launched horizontally, its initial velocity in the y is 0, because it's launched horizontally. The acceleration, though, is negative 9.81, which causes the velocity in the y to change during its path. In the x direction, there is no acceleration. So the velocity that it was launched at is a constant. So throughout the whole path, it's going to be the same Vx the entire way. Okay, Tom?
Oh, this is kind of random, but it has to do with like the whole Vy thing. It has to do with projectile motion. So you know how that Earth is like round and how it like goes down? Does that ever like affect anything moving forward?
Yeah.
Like gravity pulls.
Only over long distances, though. The Earth, and this is where calculus comes into play. If you look at the Earth on a finite space, so if you have the whole Earth and you're looking at like one location, it really doesn't look curved. It looks flat, which is why Columbus and a lot of sailors thought when you sail at the end of the Earth, it would fall off. Because if you look over the horizon, it actually does look flat. Until you look a long distance, you can see maybe some curvature, right? So on a small scale, it's not going to be affected, no. But when things are orbiting the Earth, so say you have some satellite here orbiting the Earth, and it's traveling around the Earth, it needs to take into account the curvature to keep it in its orbit. So we don't want to talk about that carefully.
Like air resistance, like would it move slower because the gravity is trying to.
Yeah, it's going to pull it down to the Earth, but there's a certain height at which the escape velocity or the velocity of the object in centripetal motion matches the gravitational pull, and it kind of balances itself. We're going to get to that this year for sure. That's going to be when we talk about celestial movements, so heavenly bodies moving. So the Earth, the Moon, the Sun, stuff like that.
We
should,
It's a very good question, though.
go back to chapter 1, because that was nice and specific.
No, but for another reason.
Wait, like, this is kind of off topic, but it kind of goes with this question. Like, is there like a certain point when you like are off Earth that like the gravitational pull just
Sure.
stops?
Absolutely.
What? So you just get out of this, like,
You
get
escape
out of
what's
like
called
a
the
certain
Earth's
like,
gravitational pull.
yeah, then you're just like gone out of it.
So, for example, when a rocket is being launched into space, it breaks what's called, it means they have escape velocity, a velocity that the object will take for it to escape the gravitational pull. Once it's outside of that pull, then it's not going to be pulled back in again.
How did they come back in?
They have thrusters on the rocket. They're like rocket propulsion devices at the bottom of it, and it like turns on the rocket propulsion, and it will turn around and make it back through.
Wait, but then just right when you get into the gravitational pull,
It'll pull
so,
you
like,
they shut them off.
back.
Well, once they get into the pull of the Earth, traditionally they're going to let the Earth pull them back in.
no, but right away, yeah, right away, do they feel like automatically like,
No, because the acceleration of the rocket will be matched to negative 9.81, so they won't even notice the transition, as if it doesn't happen. Here, man, if you want to study this kind of stuff, these are awesome questions, guys, by the way. If you want to study this, you want to look into physics and like work for NASA and stuff, it's a good field to get into. NASA's a little bit downturn now, but it's still, I mean, it still is applicable. NASA's not as prominent as it used to be. Okay? But this is a good topic. You might want to study astrophysics. That's the real topic we're talking about here. And we're going to study astrophysics this year, but we're only going to look at like a chapter or two. Okay? But all these classes, guys, all these topics we're learning, projectile motion can be its own course in entirety, in its own entirety. What am I looking for? Yeah. So you can study the whole course. Like I took a course called Dynamics in college. Dynamics is the study of motion, which is projectiles really. A whole semester on this topic. But you go into a lot more detail, you use calculus, you do a lot more math behind it. You can take astrophysics, you can take electricity and magnetism as a physics course. I mean, you can take modern physics, quantum physics. There are so many types. What's my favorite?
Yeah.
Probably this one we're doing now, projectile motion. I love dynamics.
Why?
Um,
What do you like dynamics?
I like teaching it, but it's one of the tougher ones to teach. Especially if you're teaching it and say you haven't done trig yet, like you know, I haven't done trig yet, that makes it a lot harder to teach this topic. So it's a challenge for me too. Learning it though, I like it. The problems for me are very easy to do this, and I think they're really applicable. The teaching can be a little.
Are you like that? Because they're applicable.
Yeah, because they're real life. For example, like I can watch somebody on TV, like a punter kick a ball, and know exactly the mechanics behind everything that's going on in the pen. Like the hang time, calculating it, I can find the initial velocity, the angle, like that kind of stuff. Like if I'm playing golf, and I want to hit a certain distance, I can know how high, what angle to use. So if I want to use for a 3-iron or a 9-iron, I mean, yeah, I mean, I do it in my head, but I'm not going to like, sit here and do it like that.
Do you know how to, like that movie where they go to the casino? 21? Yeah.
Yeah, I know I count cards, but I don't gamble.
I feel like you count numbers.
I don't. I'm not a gambler.
No, how do you know like you cards?
I've been to Atlantic City.
It's not hard.
Start writing this while we're talking.
Oh my god, I love gambling.
Start writing this while we're talking. Now, I've been to Atlantic City and stuff, obviously,
No,
I'm
it's like
21.
I love
Yeah.
gambling. How do you
Uh,
know? That's a big deal.
Did you guys answer this already? Was
27?
the other class answer?
28 maybe. No, you're 29.
29.
36?
31. 31.
29.
Somebody said it already, but I'm just saying, y'all everybody.
Okay,
You know who's 28 is skill filling?
Is she?
Yeah. So if you're 28, you should like be friends with her.
Wait,
Okay.
so
I graduated from college in 2008.
But
Oh, you're 3 years older than my brother, 28.
Yeah. No,
No,
he's
29.
younger than that. Yeah, you're 26?
26.
Wait, you're
Okay, I was the first one.
Yeah, you're only 3 years older
You're
than
1 year older than my brother.
When I
He's
started,
older than 3 years older
when I
than
started
you.
teaching,
He's younger than you.
when I started teaching in DC, I had one student actually in DC when I started teaching that was like, I think 20, and I was actually only 22. So that was kind of weird. But
That's
You were
your age doesn't matter, you guys. Like, I mean, I went to school, I've been to school now. I went to Villanova. I studied at Villanova Engineering, undergrad. Then I got my master's there. Then I got another master's in DC. So your age doesn't matter. If you do well in school, you can, what's that? been in school since until through I was 25. But last year I didn't go to school. So when I
Oh
have-
my god, so you're so
When were you
young.
born? What day?
You're the same age as my brother.
July what?
First.
July 23rd.
Do you know Tom Cruise's birthday is July 3rd?
Is it really? How did you
Yeah.
know that?
Because my cousin Nick's birthday is July 3rd.
That's kind of weird. You just knew it.
His wife.
He's trying to avoid a sticky situation. Let's get it.
I thought I knew Tom Cruise because he's known to be a little bit crazy, and then Mission Impossible and stuff.
Oh yeah, he usually gets really crazy.
And now that Surrey is our neighbor.
She lives in my building.
What?
You live, wait, you live in?
So she likes to ask.
Because I saw.
You live in that building?
You're not. You're in?
You live. Wait, who does? Wait, someone else lives there. Wait, have you seen this house?
I hope we're writing, guys. I'm sorry about
Wait,
that.
she's all. So you see her or not?
Tom Cruise's daughter.
Can I go over? Like, Caroline, let's go.
I see
stalk.
John doesn't have hair.
Leonardo DiCaprio lives in this
She's
building.
gonna go on the audition. I'd be really offended.
All right, so let's begin. First, we have a bridge with Tom Cruise on it. Now, whenever you have an object like this or a problem like this where it's a bridge or an object being launched horizontally, just draw like a cliff, okay? So Tom Cruise is on this bridge. Oops, that's not a person. I'm telling you, the smartboard is so bad in this calibration.
Yeah, blame it on the smartphone.
Just because you are not talented in the artistic area. I'll take it. And she's doing cards.
Yeah, draw around like
And
this.
then you
I would totally sit outside of Siri's apartment.
Tell me that it's so
Oh,
absurd.
it's easy, isn't it? Isn't it easy? I wasn't joking. The calibration is up. Don't worry, Erica. We're gonna waste too much time. Thank you. It doesn't move, but we'll just put a ball in it. Just put an object up there. We're not gonna draw a person. Okay, we'll model with an object. So,
I'm pretty sure Tom Cruise would be
I did calculate it. Well,
representing
see,
him
there's
with the
something wrong
balls.
with like 3 or 4 of the school. I have to do all that question.
Whose?
Now, please label what you know. The bridge is 300 meters above the river.
Eric, are you okay?
Next, where'd you lose? Well, you should have a pencil, so I don't want you to.
Yeah, I do, but I like running problems in hell. It lets me get it.
So, yeah?
When you call me, you're like, I'm
Thank
in
you.
trouble.
Yeah.
Are you?
Next. It says he runs off the edge, so he has jumped in the horizontal direction. So imagine, I know you would never do this, but imagine you weren't going to get hurt, and there was like a diving board 10 feet below you. If you just ran off the diving board without jumping at all, your projectile or your object, your body, would just move like that, and then you would start to fall, right? So imagine you just run, and you're running, and then there's no longer a lip, and you just run right off the edge. That's this kind of problem. I want to think about an object fired horizontally. Now, it says that if he hits the surface of the water after a horizontal displacement of 50 meters, what is the velocity that he jumped with? So what I can do is I can draw the rest of this path and put a little 50-meter mark in here. Does everybody see why I put the 50 meter down there?
Yeah.
Horizontal is 50, vertical is the 300.
Sorry, bro.
Okay?
He went.
Tristan.
Because he ran.
Run, Gabby.
I know,
Air.
But he jumps. He's just.
He hits the surface of the water, down here, after a horizontal displacement. Horizontal means along the x-axis. Displacement really means in this distance in this
He's
case.
not moving any further.
So he got launched this far. Okay?
But at
Next,
the end, because it curves.
we want to know in the beginning what his velocity was.
No, wait, I have a question actually. He's jumping 50 meters out there. Do you take into account that curve?
Gabby.
Like, is he like in the air for 50 meters until he starts dropping?
The horizontal displacement is 50
That's
meters.
just the entire go.
I don't care about the length of the curve. That's a good question. Again, we're talking about horizontal displacement being 50, not the curved path being 50. The curved path being so it doesn't actually affect the problem at all. Next. Go back to your last section of notes, or the last, not section, but the last thing you wrote down above that. In the beginning, we called this, instead of V, what did we call this?
V1, Y, no,
No.
VX.
VX, right? Because remember, he was moving only horizontally here. So we're really searching for VX. So for this kind of a problem, what I want you to do is the following. Break it into the Y direction and the X direction. We're going to be using tables to organize our setup here.
I don't like that.
And it makes it a lot easier for us. Now, in the X direction, what is the displacement in the X direction? How far, Steph?
50.
Good, so let's write X equals 50 meters. Bless you. In the Y direction, Erica,
300 meters.
down. So,
Negative.
Oh,
negative.
negative, sorry.
Sorry.
So the Y, now notice people, notice. We've always called displacement X. This whole year so far we called it X. Suddenly I'm using Y, and I have to do that. Because if I call this X, I'm not going to know which X I'm talking about. This we call Y, it still means displacement. Is that clear? This Y here is displacement. Why is it? Because that means distance, remember. D is always distance, we call that.
That's still.
That's
Still distance. Okay. Just trust me, this is common usage of physics. We're going to stick with it. Now, in the Y direction, what is my acceleration? In the Y direction.
9.81.
I have a problem. I don't know whether, like, how do you know it's not AX?
AX is in the X direction, the acceleration.
0.
Which way does gravity pull?
Down.
Down, right?
Or towards?
Is that vertical? Left and right is horizontal. So since gravity pulls down, we put it in the Y direction. And remember what we said a minute ago, guys. In the X direction, there is no acceleration. There's nothing that's, once Tom Cruise runs off the bridge, there's nothing pushing him forward anymore. His momentum is carrying him, sure, but there's no force pushing behind him that propels him forward. Whereas gravity is a force pulling you down. That's why there's acceleration in the Y. But in the X, there's nothing propelling him forward. So he's just going to carry with his momentum. But again, there's nothing pushing him forward. He's not wearing a jetpack with boosters pushing him that way. Okay? Maybe he is in Mission Impossible, yeah. You never know.
So if we get a question where it's like the wind is coming behind him like 20.
That would be an acceleration, yeah.
So you put, instead of 0, you
Well, you put whatever it is, whatever it happens to
Good
be.
job.
Good, you're
Can I go take a break?
We're gonna work a little longer, then we're gonna take a break.
Can I go to the bathroom?
No,
I need
Seth.
a break for
Just
it.
wait.
Okay, in about 5-10 minutes, we're gonna finish.